So the first synaptic transmission mastery question was, what are the characteristics of chemical and electrical synapses? Electrical synapses are gap junctions. We've already run into those, so this is actually partly a review for you guys. They tend to connect muscle cells, and they are made up of these hemichannels, one in each membrane of two adjacent cells. They come together and they form a channel that cause the cells to communicate. So because this channel is just a big hole in between the two cells, the communication is bidirectional. Ions or whatever can flow from this cell to this cell through this channel, or they can flow the other way, either direction. You will also note that other things can get through these channels too. They are huge, like nutrients, metabolites, and water. So those are characteristics of electrical synapses. Chemical synapses, there we go, here are connexons and the communication with the nutrients and water, etc., what I just said. And there is no synaptic delay associated with this, and we'll talk about the synaptic delay in a second. Okay? And again, most commonly in muscle. Chemical synapses are unidirectional. Okay, so this is the way that they work. Generally, you have a presynaptic cell, like a neuron, and then a neurotransmitter is released into a synaptic cleft. The neurotransmitter binds to the postsynaptic node, or the cell, or the postsynaptic membrane, and an action potential is generated. This is unidirectional, presynaptic to postsynaptic. It doesn't go the other way. Okay. So typically you'll have an action potential in the presynaptic axon terminal that will result in neurotransmitter release. That neurotransmitter goes into the synaptic cleft, which is a very narrow space in between the two cells. You'll get binding to the postsynaptic membrane receptors, that will result in the, here's our neurotransmitter, and it binds, and that will open a channel and allow usually sodium to flow in, and sometimes, often, potassium also to flow out, but the net effect is to depolarize the membrane. And that will depolarize the membrane, as I just said. Okay. Those are directly coupled synapses where the receptor is the same as the channel. The classic example of that is the nicotinic acetylcholine receptor and the neuromuscular junction. We also have indirectly coupled receptors where we have usually G proteins involved, where you will generate second messengers, and those second messengers will result in ion channel opening, the channel being separate from the receptor here, okay? And then the ions will flow and you'll get depolarization. So this is the way the process usually works. Just to review, and again, this is very closely related to the one of the questions that you got asked as a part of your session exercise for the case. You have an action potential. Well, first of all, you'll note you have a neurotransmitter that is synthesized and stored in synaptic vesicles. In the case of the neuromuscular junction, that would be acetylcholine. You have an action potential that propagates down to the nerve terminal here, down the nerve axon. You have that opening voltage-gated calcium channels. These are different from the ones that we learned about in muscle, the L-type and the T-type. These are N-type neuronal calcium channels. But they're voltage-gated just like the other two types. They allow calcium influx, and that allows your presynaptic vesicles to merge with this presynaptic membrane, and you get exocytosis of the neurotransmitter into the neuromuscular junction. You should note here that there is, again, a synaptic delay, as I said earlier, with chemical that isn't there with electrical synapses. That is mostly due to the delay between when this depolarization takes place and these calcium channels open, and it's about half a millisecond or so. The synaptic cleft is only about 200 angstroms, but it can be up to a micron or more in the autonomic nervous system, which we already covered in depth as far as in vital fluids and gases. Again, a synaptic delay there due to the calcium channel, the delay between when the voltage arrives and the calcium channel opening. You have your neurotransmitter, which is released into the cleft. It binds to receptors on the postsynaptic membrane. In the case of a neuromuscular junction, this would be the skeletal muscle membrane in the motor end plate. Remember, the postsynaptic membrane in skeletal muscle has a special name, the motor end plate. And the receptor in skeletal muscle would be the nicotinic ACH receptor. Just to remind you guys, the nicotinic ACH receptor is not the same as the muscarinic ACH receptor. Muscarinic, the ones that we learned in association with skeletal, cardiac muscle, those bind acetylcholine, but they have different actions. Remember that receptor actually downregulated the adenyl cyclase, so you got less cyclic AMP generated. This receptor is different. It's a different ACH receptor. It is a directly coupled synapse in the neuromuscular junction where the nicotinic ACH receptors are. That is a case where the channel is actually the same as the receptor. So the channel is the nicotinic ACH receptor. It binds ACH, it opens up, it lets sodium in and potassium out, net effect to depolarize the membrane. And the membrane voltage goes up due to the fact that you have opened the postsynaptic channels. And you get depolarization of the membrane, which causes sodium channels to open. And if this hits threshold, if it opens enough sodium channels, you generate an action potential, and it propagates away from the synaptic cleft, or in the case of skeletal muscle, the neuromuscular junction. Okay? So we have excitatory or inhibitory synapses. You guys should know that by now. We're going to review that. Here is our second mastery question. Otherwise normal patient. I did not say this. Remember, this ended up as a question on the quiz before your session, I did not specify that it was an otherwise normal patient, nor did I specify that it was a toxic dose of acetylcholine, so I have revised this to make it as I intended it. An otherwise normal patient ingests a toxic dose of acetylcholinesterase inhibitor. What would you expect to see due to the effects upon the neuromuscular junction? Of course, the acetylcholinesterase inhibitor would prevent the breakdown of acetylcholine, because the neurotransmitter, ACH, would remain bound to the receptors for a long period of time, the receptors would desensitize and the muscle would cease to contract and you would get a flaccid paralysis. So just to remind you guys, our ACH is our neurotransmitter. This is the motor end plate, which is also the postsynaptic membrane. At the top of these folds, we have the nicotinic ACH receptors. At the bottom of this junctional fold, we have the acetylcholinesterase. And and again, it is a directly coupled synapse. So you inhibit the acetylcholinesterase, the ACH, the neurotransmitter remains around too long, the receptors desensitize, and you get a flaccid paralysis. Certainly by the time you see the patient, that's what you'll see, okay? So, third mastery question, what is most likely to cause the threshold potential to increase, become less negative? In a synapse, these are the things that influence the threshold potential. If you open more potassium or chloride channels, as you may find in an inhibitory synapse, that will pull your membrane potential down back toward rest or lower in the case of the potassium channel. So the Nernst potential for chloride is the resting potential in nerve and skeletal muscle. Anytime you move off of that resting potential, let's say in a synapse where you're trying to depolarize the membrane, the chloride will pull you back down toward rest and resist that change. And as a result of that, you have to open more sodium channels in order to get your action potential to fire. And the only way to do that is to get the voltage higher. So it requires that you get to a higher voltage in order to generate an action potential. If you have a high chloride permeability, that is a lot of open chloride channels, or if you have a lot of open potassium channels, then obviously your membrane is being pulled down toward the Nernst potential for potassium, which is minus 95. That also makes it much more difficult to depolarize the membrane. You can change the number of sodium channels. For instance, local anesthetics typically block sodium channels. That effectively reduces the number. And so what you have to do is open a higher percentage of what's left in order to get an action potential to fire, which means you have to get to a higher voltage. And once again, the rate of depolarization also affects this. If you depolarize very rapidly, the threshold potential is actually more negative. That is closer to the resting potential. It's easier to fire an action potential. If the rate is much more slow, 1 millivolt per second would be extremely slow, then your threshold potential will become much less negative. That is much closer to 0, or it will increase, as we typically say. One thing that threw people with this question was the term less negative. I have been using that ever since Vital Fluids and Gases. It's all over my notes and in my videos. You may wonder why I don't just leave it as increase the threshold potential. The reason is because, technically speaking, you have a 0 potential difference across a membrane when you're at 0 millivolts. And of course, when that potential difference goes up to plus 70 millivolts, then you have a bigger potential difference. True, everybody accepts that. The problem is that if you're an engineer or you're used to working with electricity, you might say that the potential difference actually got bigger if you go to like minus 82 here. And the reason is because you've actually generated a big potential difference across that membrane. It's just that the inside has become more negative in this case instead of being more positive in this case. So technically speaking, the potential difference has gotten bigger the more negative you go. And so this gets to be, confusing, because if I say you've increased the voltage, most people would think, okay, well, I went from minus 80 to minus 55, or I went to a less negative value. That would not be confusing to a lot of you. But there are people out there, and we have been called on this, that would say the potential difference actually got lower because you got closer to 0 here if you go from minus 82 to minus 55. So in order to prevent that confusion, I use the term less negative, which is much less ambiguous. If I start at minus 80 and I go to minus 55 with my voltage, that is clearly, minus 55 is clearly less negative than minus 80. So if I say the threshold became less negative, if the threshold was originally minus 60, and I said it went less negative, that would clearly mean minus 55 is less negative than minus 60. It got farther away from the resting potential. So it's a less ambiguous way to say the term. I know that most of you are not used to hearing it that way, but I usually do try to say both, but I have to be clear. Otherwise, there are people out there that get confused by that. That's the reason why I've used it. Don't let it confuse you. An increase in the threshold potential typically means that you've gone less negative. And you should know that less negative just means that it's not as negative as it was before. It's closer to 0, okay? So some of you may have been confused by my explanation of why opening chloride channels makes the threshold potential less negative, or it increases the threshold potential. Just to explain that a little bit further, here's our normal situation for sodium and potassium. We have a gradient for potassium across the membrane, higher inside than outside. We have a gradient for sodium across the membrane, higher outside than inside. Those gradients are maintained by the sodium-potassium ATPase. Okay, so whenever sodium flows across the membrane, it's pumped back out, potassium is pumped back in, all right? And the gradient is maintained. So the gradient for potassium, maintained by that pump, determines what the Nernst potential is for potassium. So we can plug and chug into the Nernst equation, and we'll get a Nernst potential of minus 95. Okay, same thing for sodium. We can plug sodium concentrations in here. The sodium-potassium pump establishes the gradient. The gradient gives you a Nernst potential of plus 60. The problem with chloride is that it is not actively transported in most tissues. And because of that, it just flows however it wants. So if the inside of the cell is negative and the outside is positive relative to the inside, then what's going to happen is chloride's going to move. And it's going to move across this membrane and equilibrate until it stops moving. Okay, and because I'm more negative inside than outside, there'll be more chloride here than there is here. Negative charge here will repel the chloride ions. There'll be more on this side than this side. Okay, so chloride flows until it stops flowing. Well, when does it stop flowing? It stops flowing by definition when this concentration gradient is such that the Nernst potential is equal to the membrane voltage. In other words, it'll flow until I get a chloride gradient such that this Nernst equation, when calculated out, will give you an equilibrium potential that's equal to the membrane voltage. And when that gradient is established, chloride stops flowing, okay, and that's where it sits, okay, and that's where it sits in excitable tissues where they sit at the resting potential the vast majority of the time, which is true of nerve and skeletal muscle, okay. So you may say, so what? Well, the minute, let's say my resting potential is minus 80, the minute I move off of minus 80, let's say in a synapse, where it's an excitatory synapse or something, and I'm allowing sodium to come in, and I depolarize the membrane, and I get an EPSP, what's going to happen is the voltage will go up, chloride will start to flow. If I make the inside less negative, chloride will start to flow into the inside of the cell, adding negative charge to the inside and trying to make that membrane voltage, trying to bring it back down to minus 80 when it will stop flowing again. So the more open chloride channels you have, the more chloride flows into the cell, and the more the chloride tries to get the membrane back to minus 80, the original resting potential. So it's resisting the change in voltage, and because the chloride resists the change in voltage, you have to open more sodium channels to overcome that. So the more open chloride channels you have, the higher or the less negative the threshold potential, okay? And the harder it is to generate an action potential. This is the way that inhibitory synapses work. The vast majority of them work by opening chloride channels, and those are pharmacological targets, which is why we teach this for what it's worth. Okay? All right. That's it for this video. Thank you for your attention, and we'll start the next video. Thanks.